So today we're going to go ahead and talk about evaluating the definite integrals. And I want to make sure that you understand what we mean by this definite integrals versus the indefinite ones that we were doing before. So when we had indefinite integrals, that's where we had no bounds. If we have a definite integral, that means that we have an upper and a lower boundary. So we have values here. And when we're taking that area under the curve, we're looking for just that area that exists under that curve between that A and that B value. So we played with this a little bit where I have my A and my B. A little bit. We're going to revisit the fundamental theorem of calculus, which we talked about the lesson that we did when we talked about the antiderivative. And we'll go ahead and look at the fundamental theorem of calculus from a different lens today. Okay, so here we are again. A definite integral has an upper and lower bounds. A definite integral represents the area under the curve on this specific interval. All right, so when we review, we can talk about what this looks like pictorially. And we can say, if I'm looking for, and remember, this symbol is the same as the limit as the change of x approaches 0, where we talked about the sum. I didn't mean to do a curvy there. The sum of all the rectangles where we had my function of x times my change in x. And we had all of those boundaries from my A to my B, adding up all those rectangles. Now when we talk about this, from 0 to 12, here's my boundary from 0 to 12, adding up that area under the curve. So go ahead with your partners. Why don't you figure out an equation to represent, and since there's a circle there, go ahead and keep it in terms of pi. But come up with an expression to represent this area under this curve. On your mark, it's at talk. Do we agree? So in green, I have my area of the positive curve. Semicircle, so it's half pi r squared. My r is 2. I divided my trapezoid into a triangle or a rectangle and another triangle. So here's 1/2 base times height. Here's my area of that rectangle. And here's the area of the second triangle. What's in red here is negative 1/2 base times height. Here's a second triangle, 1/2 base times height. I'm subtracting that whole value. So this is worth 1, this is worth 3, so I'm subtracting 4. This negative 4 crosses out these two. So this positive 4 and this negative 4, and I get 2 pi plus 1. So doing this on a graph with a shape, tedious for sure. So what we're going to end up doing is having a formula, calculating the integral, and then putting in our boundaries and seeing what we end up with after that. Here's a question for you, though, to ponder. Take a look at this statement here. What if I had this integral, and I'm curious how you think that compares to this integral? What do you think is different, and what do you think their relationship might be? What do you notice? So from this one, I go from 0 to 12. What do you think happens here? Yeah, check it out. I go from 12 back to 0. Thoughts about what you think that result might be? What do you think? Well, let's go backwards, right? So if we're moving this way, this value here, instead of being negative, what's it going to be? Yeah. And these values here, instead of being positive, what do you think they're going to be? Yeah, negative. So if I wind up with this 4 that represents my 1 and my 3, and I represent that moving the other way, and because I'm moving right to left, this 5 that I had here, and this 2 pi, now I wind up with negative 2 pi minus 1. So the inverse. Kind of cool. All right, so we're going to talk about some properties for definite integrals. We can add these to your list of tricks that you know what to do with. If I am coming up with this area under the curve from A to A, what do you think that means? What is my boundary? Go back up to your graph. If I was going from 1 to 1, or 2 to 2, or 3 to 3, or 4 to 4, 5 to 5, how much area would be under that curve? Exactly. That's a big 0. When you are finding the area under the curve and you don't have any width, any space, that's going to be 0. Typically, when we find our area, I want you to keep in mind that we're typically talking about from A to B of f of x. When I reverse those and I'm going backwards, what did we find up here was true? It ends up being the opposite of the integral of the first. Whenever you have a definite integral and there's a constant involved, that constant is going to move outside of your integral. And just like everything else that happens with a constant, he kind of hangs out and waits to be a part of what's going on. If you have intervals that are adjacent, what does the word adjacent mean? Next to. And we can see here that A is less than C, which is less than B. C is between A and B. So if we talked about them on a number line, when we're talking about those intervals that are adjacent, no points are left out from A to C and then from C to B of this same function. What we can do then is just take the integral from A to B of f of x. So what's interesting is you'll find we can add them together and subtract them. Both those properties exist. All right, so our next property for our integrals is if I'm taking the integral of two functions that are being added together, I can break them apart and find the integral of one and add it to the integral of the other. And if this is true for addition, guess what? It's also going to be true for subtraction. So remember, the integral sign is going to be that operation that takes us from our rate back up to our original equation. So if we have a graph that we're given, or if we have a function that we're given, that function is our rate of change. And that accumulation of that change represents the total amount of whatever we're measuring, and that's what that area represents. So I love that trip project because we keep going back to thinking about how many miles total did you drive. And when you graphed your speed over each of those intervals, you were accumulating up how many miles happened at that speed. So we can talk about each of these different pieces of what you're doing, taking the miles here, taking the miles here, adding them up. If you did that whole trip twice, imagine that K being that coefficient, right? If you did that whole trip backwards, right? If you never went anywhere, are you with me on that? So your trip project really was a great example that we can keep coming back to and talking about what it is that we're talking on each of these conversations. All right? So on this side, we can go ahead and work through some, okay? So what's interesting here is I want you to take a look at each of these integrals. F of x dx is equal to 4. The area under the curve from negative 2 to 1 is 4. The area under the curve from 1 to 5 is negative 3. Keep in mind these are both the same function, f of x. Over here from negative 2 to 1 of g is going to be 8. So same interval, different function, same functions, different intervals. So what we can do here is use each of those properties that we did before, or that we just have on the other side, and figure out what it is they want us to do. So if I'm looking for 5 to 1, which way am I going, forwards or backwards? So if forwards from 1 to 5 is negative 3, what is backwards going to be? That's going to be our reverse, which is going to give us a value of positive 3. And I know that the interval from 1 to 5, if I take the opposite, and therefore I get an answer of 3. All right, now I'm talking about f of x. I don't have a value from negative 2 to 5, but I do have the interval from negative 2 to 1 of f of x is equal to 4. And I know that the interval from 1 to 5 of f of x is equal to negative 3. So how about this interval here? What do I do? What do I do with those two values? What do I do with them? I'm going to add them together. And I get positive 1. With your partner, take a look at this one. Take a look at the front and see which rule it fits. Go. All right, so I can break these up and figure out the integral of f of x is 4 along that interval of g of x is positive 8. So I can add them together. The area under the curve of these two functions from -2 to 1 is equal to 12. Okay, and that's this property here, where I can, along the same interval, take the integral separately. So I heard a couple of people being like, wait, aren't C and D the same? They are. That's a typo. Would you change this to a 0 for me? So what's going on with this one, do you think? If we didn't change it, you're like, it's the same answer. I know. Once we change it to 0, what does that mean? Do we have any of that information? We have other pieces, but unless somebody gives us a graph to look at or some more intervals, cannot be determined. And sometimes that's so frustrating for me because once they introduce that, I'm like, oh man, that introduces that extra question. You're like, if you know you have to find an answer versus wait, there's no answer, you're like, all right. What do I do with this constant? Yeah, he's going to come outside. So it's going to be 3 times the interval from 1 to -2. Backwards, right? Of f of x dx. So it's going to be 3 times. So from -2 to 1 of f of x is positive 4. So what are we putting in here? -4. And that's our -12. So f of x and g of x, I'm getting all upset because I don't have g for any interval other than this one. So I'm about to write cannot be determined, but that's not the answer. What is the answer? How come? Because they didn't give me any kind of interval, so there is no area under the curve on that interval. All right, so we're going to start talking about this fundamental theorem of calculus, and there are a couple different ways. If you want a page back in your notes, we ended up talking about it, and I'll pull up the notes for you. We ended up talking about it in this conversation when we said, okay, the derivative of the integral is equal to that original function. And then we ended up talking about how they're inverses of each other, and this accumulation function and is an antiderivative. And we talked about how these two symbols do that to each other. And then on the reverse of this sheet, we ended up talking about a couple different properties where we talked about if we had a fixed value to a function, how we applied the chain rule. And if we had a couple different functions, we ended up taking the difference of those. And because we were taking the derivative, that chain rule still applied. So we're looking at, again, another variation of the fundamental theorem of calculus, and this is the one that says if x, or if f is continuous on this interval, and I'm taking the integral of, and remember, this is a rate function. It's already the derivative. So if I'm doing this, I'm looking for my original function. I'm looking for my area under the curve. I'm looking for my output, big F of x. So if that's easier for you to think about as total gallons, total miles, whatever, I'm using this symbol that represents find the sum and take me back up to the level before, take me up from my rate. So what we're going to do is we're going to go ahead and take my original function, the output on my upper bound, minus my original function, the output on my lower bound. So remember that capital letter F is what takes us up to our original function. That's how we integrate. And then we're going to go ahead and find those definite values. Before, we've been integrating without having this a and b. Now we're going to integrate with the a and b. So step one is going to be to use those integration rules that you have. So ignore these bounds for the first. So do me a favor with your group, remind yourself how to go ahead and integrate 4 minus 6x. Go. All right, so when we're coming back to this, this is our integral. Anybody want to shout out that I'm missing something? Yeah, you're going to talk about where's your C. So here's what I want you to think about. Whatever constant value I had on this lower and upper boundary, when I subtract them, those C's would cancel. Are you with me? Think about it for a minute. If I'm subtracting the one function from the other, and this function has a constant of 5, and this function has a constant of 5, won't those two constants cancel? You with me on that? Because what I'm doing is, in order to find that area between those two, I'm taking the output. Let's say that you just wanted to know how many miles you drove during the middle part of your trip, right? You would take your odometer reading at the end of that range and the odometer reading at the beginning of that range and subtract, and that would be that middle. Are you with me on that? So that's what we're doing with these functions. We're subtracting them. So whatever constant value I have here, I'm going to have here, and I'm going to subtract it. So when you're thinking about, hey, where's the plus C, the thing that we're going to do next, those C's will cancel, so we get to not include them. And we're going to change our notation of how we write this, and we're going to say, in order to find the definite integral of 4x, 2x squared from 2, we're divide by 2, we're going to draw this vertical line, and we're going to talk about how we want it on this boundary. So what we need to do now is find the output of this value minus this function with the output of this input value. So here is our b, here is our a, and if we're finding that integral, that's that area under the curve between b and a, we're going to go ahead and figure out the output value of that function. This is my original function. So what I'm going to do is say, okay, 4 times 5 minus 6 times 5 squared divided by 2. And this is the output when 5 was my input. This is my original function with 5 as the input value. If I want to know that area between those boundaries, I'm going to then insert my a value, -2. So positive 4 times -2 minus 6 times -2 squared over 2. This is f of b. This is f of a. I don't need to worry about the constant because whatever constant value existed, it's this minus this, and it cancels out. Now, I gotta be honest with you, we probably should have simplified this and just called this 3x squared. That would have been easier. Don't worry about it. You'll make up for that here. Here's 20 minus, we okay with 75? Minus -8. -2 squared is positive 4, so that's minus 12. -20 75 is -55. And this is going to be -20, so it's going to be plus 20. How'd you do? Do we agree? Somewhat. So what we're going to start doing is jumping in and starting at this step here. Because once you integrate it with your bounds, there's no need to calculate this indefinite integral because we do have these boundaries that we're going to figure it out. You ready? So when we go to integrate this, it might help us to go ahead and rewrite this as x to the 1/2 power minus x to the -2nd power. If it's easier for you to rewrite that, go ahead and do that. Add 1 to the exponent. X becomes 3/2. Divide by the new exponent. Doesn't that put a 2 here and a 3 here? Minus, add 1 to the exponent, x to the -1. Divide by your new exponent. And we're going to be calculating that on the interval from 1 to 4. If you want to clean this up a little bit, you could call this 2/3 x to the 3/2 power. And this becomes plus 1 over x from 1 to 4. This negative exponent sends this guy down, and these two negatives cancel out and make a plus. Sound okay? So we'll do our upper boundary first. 2/3 times 4 to the 3/2 power plus 1 over 4. That's our f of b, our original function with my upper boundary as the input, figuring out what my output is, minus 2/3 x to the 3/2 power plus 1 over my input value. That's my original function with my lower boundary as the input. Now I went ahead and painstakingly substituted all those x values in, but let's be honest. This is 2/3 plus 1, right? 1 to the 3/2 power is 1. 2/3 times 1 is 1, plus 1, right? You with me on that? Square root of 4 is 2. 2 cubed is 8. 4 to the 3/2 power. Sounds like 8 to me, right? 2/3 of 8 is 16/3 plus 1/4 minus 2/3 plus 1. If you want to go ahead and enter that into your calculator, you're welcome to it. If you're like, the fraction math is killing me, lady, don't make me do it. It's AP season. 16 divided by 3 plus 1 divided by 4. Math fraction, that's 67/12. Minus, if you're fuzzy on 2/3, plus 1. 1 and 2/3, math frac, 5/3. If you take that answer and you go up on your calculator, 29/4. Oh, I should be subtracting. I don't think I subtracted, did I? Nope. 67 divided by 12 minus 5 divided by 3. And then I did it twice. I pressed it twice. Why did I do that? I should have just used my brain. That's why. 47/12. Does that sound better? And it's important that you know what you're finding. What does that mean? That is the area under this curve of this equation from this to this point. What's the total accumulation? Kind of cool. And don't forget our trig functions. How could you? Constant stays out there. What's the integral of sine? It's cosine. So it's going to be 4 times. Isn't it negative? Yep. Now I gotta squeeze my negative in. Four times the opposite of cosine from 0 to pi over 2. I'm going to let you and your partners figure out. Insert. Bring that trig back up to the front of your brain. Your mark it, set, go. Do we agree? So when I put pi over 2 in, the cosine of pi over 2 is 0. So the opposite of 0 is 0. 4 times 0 is 0. This whole goes away. My lower boundary is 0. The cosine of 0 is 1. The opposite of 1 is negative 1. Negative 1 times negative 4 is positive 4. We good? Next one, super easy. Turn to your partner and go. Find the trick. Go. Veronica and Mesa are like, can we have a test of these? Because that integral, right? And you can see why, if you want to painstakingly go through and see why, we can go ahead and do that. Sure, no, that is fun. Because the integral of e to the x is, of course, e to the x. We don't have to worry about the plus c. And we're doing it from 0 to 0. So we're going to do e to the 0 minus e to the 0. Are you with me now? Anything to the 0 power is 1. Do I have to still keep going? So it's kind of nice that we can see that put into effect and proven for us. Okay, so here is your classwork / homework. And it's kind of a fun puzzle. I think it's kind of cool. So what you're going to be doing is making a pattern. So finding the integral of each of these and then coloring in the box of that answer with the pattern that you see shaded. And the one hole punch goes through, but I think you can still figure out what you would need to color. If you're struggling, then that's fine. I do want this turned in because I want to give you a homework grade. So you have 40 minutes to work on it. I think that's more than enough. And then there's a couple on the back. So start working now. If you're a friend who wants to see me for a copy of the test because you're turning in your review packet, we can have that talk too. Are we all good? Any questions before I? Okay.